So let us recall what we did in the previous lecture. In the previous lecture, we have talked about the compact matrix space. So what is the definition of a compact matrix space? It says that totally bounded plus complete. So any set which is totally bounded plus it is complete, and that set is called the compact. We know that the totally bounded means a set which covered by a finite union of AIs, where each of this AI having the diameter is finite or given diameter, and the complete means every Cauchy sequence is convergent. We have seen certain examples of a compact matrix space. We have proved that the following results into the previous lecture. The first result was that if X is compact, if and only if every sequence in X has convergent subsequence. So every sequence has a convergent subsequence. That results we have proved in the previous lecture. The next result we have proved that if X is compact and A, which is a subset of X, A is closed, implies A is compact. That means a closed subset of a compact matrix space, closed subset of a compact matrix space is always compact. And A is compact. This is in general true, that is X is compact. Then it will implies X is closed, which is always true. So if you want the converse of this result, you require that this X should be a subset of some compact matrix space. Then we have proved that if X is compact, will implies that X is closed and bounded. The converse of this result is not true. The example is L2 space, that is a square summable sequences. In that you will have defined this set A, which is set of all EIs, where EI is the ith element, it will be 1, otherwise it will be 0 for Ln. Then this set is a closed as well as bounded, but it is not compact because it is not totally bounded. The question is when the converse is true. That means when I can say that a closed plus bounded is compact. So under the real line, this is true. If X is a subset of a real line, then this result is true. That means if you have a set E, which is a subset of R, which is a set of all real numbers, then you can say that E is compact if and only if E is closed plus bounded. We have proved this results into the previous lecture and discussed certain examples based on compact matrix space. In this lecture, we will further develop certain results on a compact matrix space, and that results gives you the equivalent condition of compact matrix space. So to define that one, to discuss that one, we'll define this open covering of any set. So let X be any set. If you have X is a set and a family, that is script F, of a subsets, that is AI of X, is said to form a covering of X if X is a subset of union of AI, where AI is belongs to the script F. So the script F is a family of subsets of AI, subsets AI of X. And if you can have this X will be covered by this family, then I can say that this family, that is script F, is covering X. And each of these AIs are open, then it is called the open covering. It's cover the set X. And if this each of AI are open sets, then it is called open covering. So that is the next. We can say if X is a metric space, and each AI are open sets, then F, that is a script F, it's called open covering of X. That means it has to be satisfy this. And plus this each of AI are subsets which are open. So therefore I can say X is covered by open covering. Open, it's covering. So X is covered by this AI. And next definition is a finite subcovering. So if the finite subcovering, that means this covering F or this covering F has finitely many sets which cover the set X, then it's called the finite subcovering. So finite, if the finite subcovering subfamily of script F cover X, then the finite subfamily it's called finite subcovering of X. That means there exists some F1, F2 up to Fn belongs to X, sorry, belongs to F, script F, such that this X is covered by finitely many members of this. Then I can say that X is, the script F has finite subcovering. Script F has a finite subcovering. Okay. So this is the definition of a covering, open covering, and finite subcovering. Okay. Now we will have the next result which deals with the compactness as a subset of R, and we have done that if any subset of R which is compact, it is equivalent to saying that it is closed plus bounded. So let F be a bounded and closed subset of R. Otherwise I can just say that F is a compact subset of R. That is also equivalent statement to write this. Then prove that every open covering of F has finite subcovering. That means every open covering has a finite subcovering if it is a closed plus bounded. So ultimately I can say that if F is compact subset of R, then every open covering has a finite subcovering. Let us try to discuss the proof for this. Since F is a closed and bounded subset of R, it has to be covered or it has to be a subset of some interval I1. So let's start with that. Since F is closed and bounded subset of R, there exists an interval I1, which I can say it is the interval of the form AB, where A is less than B, such that F is a subset of I1. See, if it is clear that this, what I want to prove is this F has a finite subcovering. If I can prove that every open covering of I1 has a finite subcovering, then F will also have the finite subcovering. Every open covering of, since F is a subset of I1, so if I can prove the result for F, it is equivalent to proving the result for I1. So that is what we will do. That it is clear that if every open covering of I1 contains a finite subcovering, then every open covering of F will contain finite subcovering. Okay, so ultimately we need to prove the result is for I1. So now we shall prove the result for I1. Suppose not, so we'll prove by contradiction. That means suppose that I1 does not, every open covering of I1 does not contain a finite subcovering. Okay, so we'll proving this result by contradiction. That is, suppose on the contradictory that there is an open covering G of I1 which has no finite subcovering. Okay, so this is a script G I should write here. So this is open covering script G. Suppose on contradictory, we have to prove that every open covering of this I1 have finite subcovering. So we are assuming that there is some open covering of I1 which does not have finite subcovering. That means I1 cannot be covered by finitely many elements or finitely many members of this open covering. So for that I will divide this interval I1 into two parts or into two closed intervals, and at least one of them does not contains a finite subcovering. If both of them contains a finite subcovering, then I1 contains a finite subcovering. So at least if I divide this interval I1, so I have an interval I1, that is interval AB, and dividing this interval AB into two parts. The first part I will say it is I2, another part I will say it is I2 dash. If both this part I2 and I2 dash contains the finite subcovering of this G, then I1 contains a finite subcovering. So at least one of them, either I2 or I2 dash, contains a finite subcovering. Sorry, does not contain a finite subcovering. So that's we can write here, bisect I1 into two closed intervals I2 and I2 dash. At least one of this must have no finite subcovering. So at least one of them does not have a finite subcovering. Let's say that is I2. Without loss of generality, I can assume that it is I2. So without loss of generality, let I2 have no finite subcovering. Okay. So I2 does not contain a finite subcovering. Let's divide I2. So here is the I2. Let's divide I2 into the two closed intervals, I3 and I3 dash. And having the same argument, if I3 and I3 dash both of them have the finite subcovering, then I2 has a finite subcovering. But we have I2 does not have a finite subcovering. So I3, either I3 or I3 dash does not contain a finite subcovering of G. Okay, so next bisect I2 and obtain I3 which has no finite subcovering. And continuing in this way, proceeding in this manner, what will happen? We will obtain a nested interval, because the first we have started with the interval I1. So I1 is the biggest interval, and then there is a subset of that, it is I2. Then there will be a subset of that which is I2, I3, and so on. So we obtain a nested sequence In of closed intervals such that for every n, for each n, In has no finite subcovering. Each of this In does not have a finite, but this is the nested intervals. Okay, or I can say it is a decreasing sequence of intervals, and which are closed intervals. So can you apply some of the theorem which you have learned? by nested interval theorem, by nested interval theorem, it tells you that the intersection of this In will be non-empty for each n. Let X will be in the intersection of In. That will implies X will be in the each of this In. But In is a subset of I1, and I1 is a subset of union of Gi, where Gi's are that I have said that it is open covering, that I is belongs to script G. Okay, that means X is belongs to some of this Gi. Okay, so that will implies X is belongs to Gi for some I. This Gi. Now this Gi is an open set. So since Gi is an open set, so as per the definition of open set, there exists an open sphere SR of X such that SR of X is a subset of Gi. Okay. And taking this n large as much as possible. If you can take n should be large one. So I can say that, so now by taking n large enough, that means this n is large means that interval In is very small, is as small as much as possible, because it is a decreasing sequence. So if I taking this n will be large, that In will be a subset of this SR of X, and which is a subset of Gi. What does it mean? This will gives you a contradiction with the fact that In is not covered by this Gi, because here it says that In is covered by only one set Gi. So this In is covered by only one set. Which is a contradiction with the fact that In does not covered by finitely many members of Gi. But why we got this contradiction? Because we have assumed that I1 is not covered by finitely many members of Gi, or that is I1 does not have a finite subcover. So this will complete the proof that, therefore I can say I1 has finite subcover of script G, and hence any closed and bounded subset of R will have a finite subcover. Or ultimately what I can say is, if F is compact and F is a subset of R, which is ultimately it is a closed and bounded, it implies that every open covering of F has finite subcover. This is very important results. The question one can ask always whenever we are discussing any results, this is always you have to ask the question that whether the converse true. That means, can every open covering of F has a finite subcover? Will it implies that F is compact. Okay. The converse is also true. In fact, it is true in general for any metric space. That we will do it in the next. But before that, let us conclude some of the examples here. So the question is, find an open covering for closed interval AB which contains a finite subcovering. In the absolute metric or in the usual metric on R. So the question is to calculate, or first of all, can you give me some open covering of this interval, closed interval AB? Solution. Which will have the finite subcovering. So we note these things that. So can you give me some sequence of intervals which cover this interval AB, closed interval AB? So we can have this interval. So closed interval AB is always a subset of union of n running from 1 to infinity, open interval 1 a minus 1 by n to a plus 1 by n, sorry, b plus 1 by n. So this is the open covering. So what is your open what is the family of interval which is open covering? I can define as this: script f is equal to set of all intervals b plus 1 by n, where n is belongs to n. So this is the family of intervals. So I can say this f, script f, is an open covering of f. Since this closed interval AB is a closed and bounded interval, so that means it will have a finite subcover. That means you can cover this interval AB with the finitely many members of this family. Okay. And that you can see if you have any interval, let's say closed interval 0, 1, then you will have this intervals 1 by n minus 0 minus 1 by n to 1 plus 1 by n. So you can just write n equal to 1, then the interval is minus 1 to 2. This is the interval you have, and for n equal to 1, this is the summation from 1 to infinity. So the total interval is this. It will be minus 1 to 2. Here it is minus 1, sorry, 0 to 1 is this, so minus 1 will be here somewhere. And 2 interval is this. It's here somewhere. So this is the first interval. Obviously this interval, closed interval 0, 1, is a subset of minus 1 to 2. So this family of open intervals, which is an open covering of closed interval 0, 1, contains a finite subcover, which is exactly the one element is required for this set. So that is the theorem which we have did earlier. That is, if it is a closed and bounded subset of a real number, then it is always has finite subcover. So this script f here in this particular case contains a finite subcovering. I can write in one line only here that since this closed interval AB is a closed and bounded, the script f contains finite subcovering. And what will be this? You just pick up one a minus 1 to b plus 1. According to the value of a and b, you can have here in the particular case, in the case of 0, 1, it will cover only by one set, one member of this. Now, the next, if you drop this condition, that means closedness, if you drop that condition, or I can drop a boundedness, whether the result is still true, or that means we can we do the weaker condition and the result is true? The answer is no. For that we'll have a next example. So find an open covering of the set open interval 0, 1, which does not contains a finite subcovering. So the first question is to calculate. This is not a closed set. This is an open set. Okay. So we are dropping this condition closeness from this statement, and we have to prove that there exists some open covering of this set which does not contain any finite subcovering. So what will be the open covering of this set? Can somebody give me a script f? Open covering of this. Let's say it is a script G. So that open covering I can define like this: 1 upon n plus 2 to 1 by n, for any n belongs to n. So what are these intervals? Just look at it, these intervals. The first interval is 1 by 3, 1, for n equal to 1. Second interval is 1 by 4, 1 by 2. The third interval is 1 by 5, 1 by 3, and so on. So this is the interval, set of intervals is there. So this is so I can say that now we easily seen that open interval 0, 1 is a subset of union of this sets. So I can say n running from 1 to infinity, 1 upon 1 plus n plus 2 comma 1 upon n. So this is the open covering. It's covered because you just see the intervals. This is the open interval 0, 1. The first element is 1 by 3, 1. So this is somewhere here, it is 1 by 2. So 1 by 3 is somewhere here. So this is the first interval you will have. This will be the first interval. The second interval is 1 by 4, 1 by 2. So this is the second interval. Somewhere here it is 1 by 4. Then it is 1 by 5, 1 by 3. So it is a collection of all this, and it will reach to 0 at one state when n is large. Okay. So it is not 0 is included here. It is open. So that's why it is near to 0. So this is covered, this set. So I can say that the script G is open covering of this open interval 0. Now I want to prove that this script G does not contain any open covering. That is our objective. So we shall show that. Script G does not contain any finite subcovering. Okay. Suppose not. Suppose that it will contain a finite subcovering. Suppose not. Let us say the script G star, that is A1 B1 A2 B2 up to AN BN is a finite subcovering of open interval 0 1. Let's say this is a finite subcovering. What will happen? As you can see the pattern of the interval, how this interval is worked out. So I'm just saying that I will pick this as a G1 or any other G2 or so on. So you can pick up the finitely many members of this sets and you have put it into this set. Okay. Now what I will do is I will define if some number, let's say delta, will be the minimum of this A1, A2 up to AN. Okay. Then obviously this delta is greater than 0. Delta will be the greater than 0. Okay. And this intervals, that is A1, B1, is a subset of epsilon 1. In fact, any of this interval A2, B2 is a subset of epsilon 1. So in general, I can say AN BN is a subset of epsilon 1. This is for every n I can write, for running from 1 to n. Okay. Why? You can just see that as per the pattern of this. So I'm just saying that whenever it is finished, so it is whenever, suppose this is the minimum of all this A1, A2 up to AN is there. So here I'm taking this is the delta. So this delta to 1 will contains by all these elements or this intervals. Then what will be the part is the left, but 0 to epsilon, or sorry, 0 to delta, which we have here. And this delta to, why I have written epsilon, this is delta everywhere. This delta to 1 are disjoint. That is obvious things which we can note, that 0 to delta and delta to 1, they are the disjoint subsets. And 0 to delta is not contained in this any of this interval. So that means this G star will not cover the open interval 0 1. So hence the G star does not cover open interval 0 1. So which proves this statement that find an open covering of closed interval. So we have, this is open covering which does not contains any finite subcovering. Now we have the next result or next definition. This definition is known as the Heine Boral property. Heine Boral property. What is this Heine Boral property? It said that if you have any metric space, will have open covering, then there exists a finite subcovering of that. Okay. So this Heine Boral property says that let A metric space is there, metric space x comma d is said to have Heine Boral property if whenever a script f is an open covering of x, then there exists a finite number of sets g1, g2 up to gn of a script f such that this x is covered by this finitely many members. Ultimately, every open covering, if whenever it is open covering, will contains a finite subcover. Then it is called finite subcovering. For example, closed interval 0, 1 have a Heine Boral property, because we have proved that if it is Heine Boral property, then every open covering has a finite subcover, because it is a closed and bounded subset. But open interval 0, 1 does not have a Heine Boral property, because we have proved in the previous example that we have considered one open covering which does not have any open covering, any subcovering. Now, with the help of this Heine Boral property, we have a next result. That result is stated like this: prove that X is compact metric space if and only if it has Heine Boral property. This Heine and Boral, both of them are different mathematicians, so it has to be a letter H and letter B is capital. We'll not discuss the proof of this statement. If anyone is interested to do it in their project, they can do it. Okay, so the proof I'm making it is in project. If anyone interested, they can try to discuss the proof for this statement, that if any metric space which is a compact, then it will have a Heine Boral property. For real line, one part we already did. That is, if X is compact, then it has a Heine Boral property that we have proved in for the real line. The converse is also true, which tells you by this statement. Okay. And in some of the textbook, they are using this as a definition of a compact metric space. As I have told you, so we have now three equivalent statements regarding the compact metric space. The first statement is totally bounded plus complete. The second statement is every Cauchy sequence has convergent subsequence, and the third statement is it has Heine Boral property. That means every covering has a finite subcover. So these are the three equivalent statements regarding the compactness we have studied till now. So we'll stop for today here. Okay. If you have any question, you can ask.